你说我的 YouTube 吗？没有。哦，有了。看一下哦，我找一下哦，先别挂。应该是可以的啦。对，因为这个黑色那个里面只要有画面，然后你先帮我看一下哦。你现在有可以帮我看一下吗？不太确定。你帮我看一下，应该是有啦。对。
大家都照这样应该比较好录吧？对，就是永远都在，因为你们的也是16:9。
我们是16:9。
对啊，所以应该就是刚刚好，就不需要再调。你是没有来过的，你有直播过？
有，可是刚刚跟上次不太一样。
有，他上次来是1机，这一次变2机。
只有1机啊，只有1机啊。对啊。
有吧？应该有吧？
不，你现在能不能上线？
有。
可以哦。
可以，好，谢谢，拜拜。
可以吗？
对，因为打给朋友确认一下。
不，你目前的视野除了这个之外，
还有
一般有涵盖到这里吗？
大概到那个 ADS 那边，安培一半而已。
这里。
对。
这里一半，然后包含整个荧幕。
就是这边一点点黑板。
这边。
一点点黑板吧，大概20公分的黑板。
哦。这一段。
我基本上今后可能都尽量不用那一半。
右边吗？那我就固定。
看有没有。
抖销。
接下来绝大部分是用投影片，然后如果黑板需要补充的话，对，你们正好切到这一个线，然后这边右边可以调一下，能包含到全部的。
有，但是可能要调一下角度。对。不是，你看这样可以吗？如果说是这样的话，稍微切掉一点这个边边。
OK 没有，OK
还是要再过来一点点。
再过去一点点好了，就是投影片，投影片反而是为主。对。
这样子。
OK 没问题。
好。
这样子，你觉得黑板上跟这里面的字大小，他们看得到吗？
因为我觉得是因为它这个对焦，它会这边会不太明显，黑板会不太明显。
OK。那另外一个就是说，我其实周末我是大力鼓励他们上课上到一半问问题啦。那他们问问题是你会看得到他们打，
就是他们会在留言区打，他们会刷留言。
OK， 那可能你要帮忙注意一下，真的有需要我再重复讲一次的，就是。
好。
对。现在参加 streaming 的学生越来越少，那一部分也是因为可能网络品质不是太好吧，然后另外一部分可能是说比较没有办法及时反应，说哪里听不懂。今天试着再跟看。
拍一下，你要不要看这个黑板，这样会很清楚。如果拍动，应该会很清楚吧？因为2个画面同时拍，就是那个光不太。如果你这样单独拍黑板。
不行，这边还是太亮。对，是投影片本身太亮。 还是有点。
我应该可以调那个位元率。你们是用 OBS？
对。
OBS 里面应该设定那边可以调那个位元率。设定那边。
设定。
然后，因为我不知道你们位元率是用多少。
增加它的 dynamic range。不，我觉得这个的问题，因为是它同时两块。
对啊，应该是它对比度太强。
对啊。
平均的。
就除非你可以切换说，就是现在只看到黑板，那它就会重新调它的亮度。
像上次那个小美女会是先拍那个，然后老师如果拍到黑板，他就转过去。
也可以。
对，这样子。
但就是说你会比较 loading 比较对。不，我个人是觉得，以目前这个黑板没有打光，好像其实也录的 OK。对，我觉得其实可能不用拍，你们现在这样拍黑板 OK。
其实蛮清楚。
对，蛮清楚的。
对。
我觉得其实不用，你不用那么辛苦在那边切换。对。因为我周末再看一下那个影片，就是在切换的过程。
会闪灯。
对，会闪啊。
对，会闪灯。
我觉得不如算了，这样子应该 OK 了啦。这样应该 OK 了。
那老师，你可能黑板字要再大一点，直播的话会比较明显，因为现在问题是它可能字太小，然后不够亮会糊。就是如果是
目前这样还太小吗？
就是它是会糊在一起的。
以目前这样会糊在一起。
对。
好。
如果再大一点，应该会比较清楚一点。
没关系，我还有时间。那投影片这个字够吗？
字够，因为它够亮，所以它比较好看。
再大一点。这样 OK 吗？
应该是主要看那个吧，看一下老师你的小写部分，就是英文小写，因为像 E 跟 C 它可能会变成看不清楚。
哇，这很大字啊！
因为它像刚刚老师的大小，大概 E 跟 C 就会没办法分辨，就是这边的镜头。
这样子。
是啊。老师，你的字可以再稍微松一点吗？就是间隔再大一点点。
这样。
这样应该对，这样应该是极限的，就是这边是看得到了，但是我就不知道他们有没有办法接受。这里是
你现在没有放大到全幕吧？
有啊。
啊，你现在
就是我的电脑荧幕就是这么大，可是如果是你要用它内建的小荧幕看，应该是不行。
这个 vector 看得到吗？
看一下哦。
会不会太密？
我在想说这两期应该解决不了，所以我就看了。因为那种普通的有光的话就可以看到，这种。
This
live in Taiwan, we encounter this almost every summer.
Those are not getting
So typhoons are essentially a curl-free, non-curl-free field that we encounter on our daily life. I will come back to this in detail, but this is very iconic. So think of typhoon as some kind of giving you curl. And now you should be thinking about what type of field does not give you curl. Okay, so let's talk about the next formal definition. When we try to evaluate the curl of a vector field, essentially we are trying to calculate the net circulation of that field. What does net circulation stand for? For example, I have my vector field A. It is a function of space, of course. But if I decide I form a closed loop, just call it C, a closed loop. And I want to know if I start from a certain point on the loop, and then I'm trying to measure how much of that vector field is, well, pushing me along the distance. Okay, therefore I have my vector field making an inner dot product to
前一页或2页可以重复，因为刚刚收音有点问题。刚刚收音有问题，所以可能要重复一下。
Okay, so let me repeat. So basically, this is a movie showing you typhoon. Okay, and typhoon is some kind of field that really gives you curl. All right, so we live every day in Taiwan. Every summer we encounter typhoons. So we should appreciate typhoons. So these are like circulating fields. So this is not some field you see every day. The field circulates. Okay? So by definition, when we evaluate curl of a vector field, we're trying to see how much of that field is really circulating. So the net circulation means I have my vector field, a function of space, and if I form a closed loop, and somehow I walk on the closed loop, I start from any given point, and I want to know how much of that field is really trying to push me, right? Doing work on me. So the proper mathematical formulation is the vector field making an inner dot product with my differential length. So imagine this A is force. This is something you learned in high school, right? F dot dl is work. So this is really asking if I sit on point P and the vector field is pushing me, okay? Pushing me in the direction of dl along the closed contour, then it's giving me work. So I'm gaining energy. But the question is, if I walk along the closed loop, the wording closed loop means you start from a given point, you end up at the same point. Right? So a closed loop guarantees you start from point P, you walk along this path, but again you come back and you end up at the same point where you started. And now you have to ask yourselves, after this closed loop integration of your given vector field, and you integrate along all the differential length, is that 0 or non-zero? In the daily life, in the world that we live in, usually gravity gravity gives you some kind of force, right? So if you walk from the 2nd floor, like where we are, up to the 8th floor and come back, do you gain any potential? No. So in that case, if your vector field is so-called conserved field, like gravity, the integration over a closed loop will give you a 0. So there's no net circulation. But let's come back to the movie as I promised. Typhoon is rotating, right? It's circulating. So imagine you throw yourself or your pet into the typhoon. What is the typhoon field going to do with you or your pet? It will speed you up, right? Initially, your pet or you is stationary, not moving. Once you throw it into the typhoon field, you start to accelerate. Why? Because the typhoon is itself circulating. So that means there are some type of vector field which is rotating, circulating, so that you start from this point, and as you progress, as you walk along this closed loop, you're gaining more and more energy. So even though when you come back to your initial starting point, your energy as compared to your starting point is more. So this is non-zero. Okay? So let's come back to the blackboard. Let me just draw you an example. Gravity, right? Gravity points towards the center of Earth. So it's unidirectional. If you walk in this path, a closed loop, you have segment 1, segment 2. For example, we're starting from 2nd floor, where we are in Delta building. We walk all the way up to the 8th floor, and then we come back. So over this closed loop, I started from this point, 2nd floor. I took my stairs all the way to the 8th floor, and then I decided to come back. For this segment, I'm working against gravity. So my legs are working, right? So I gain potential, I gain height. But then as I walk down, I regain I lose my height. So eventually, in this case, if your field, your vector field is unidirectional, your net circulation will be 0. You don't gain anything by walking along this closed loop. But on the other hand, what happens if your field your vector field A now looks like that? That very much represents a typhoon, right? A circulating field. If the field is itself a closed loop-like distribution, then you walk for a closed loop. Along each segment, your vector field is giving you positive contribution. Each segment adds up. In this case, the first segment and the third segment cancels out. So you have a net 0 circulation. But in this case, each segment along the closed loop you're walking on, they all have the same sign of work donated from your vector field. So these are very two different vector fields. One is unidirectional, another is rotation. So the physical meaning of performing curl operation in this movie. When we try to perform curl operation, in essence, we're trying to extract, are there any rotational contributions within that vector field? If we have rotational contribution, let me turn off the light so you can see the movie better. Is it better? So here, I'm giving you a calculated vortex field, or like a typhoon field, if it's circulating, right? So just imagine you throw in a small particle, it will be accelerated and moves along how the field is rotating. And you're guaranteed to gain some kind of energy after one rotation. Per rotation, you're gaining some energy. And it is because this A dot dl, if A is everywhere in the same direction as your differential length, this O adds up. Nothing is being cancelled. So therefore, even though you walk along a closed loop, you start from one location, you come back to the same location, but eventually you gain in energy or height or potential. So you have a non-zero net circulation. So is that clear up to now? Are there any questions from the students online? All right. Okay, so the meaning is if we have a rotational or circulating vector field, it is a non-conserved field, 非保守场. Vortex field, typhoon, they are non-conserved because they're circulating, so your net circulation would not be zero. Okay? So in essence, the formal definition of curl operating on a vector field is you're trying to find the maximum circulation, net circulation, over a small surface area. For example, I have some vector field. I want to find the maximum amount of net circulation, so I want to know its direction as well as the magnitude. Right? After you perform a curl, you have a vector. So it has its direction, it has its magnitude. So I want to know along which closed loop would I arrive at the maximum amount of circulation or gaining in energy. Okay, so that's a definition. So if you perform the curl operation on the vector field, if that vector field has some component that is circulating, you can find it by performing this operation. On the other hand, if you have like gravity conserved field, 保守场, you don't have net circulation, right? So again, the definition is you're trying to find the maximum net circulation per unit area, and the direction gives you the sense of rotation. So we use the right-hand rule. For this case, we have a closed loop, so the direction of my circulation is given by the thumb, but it's actually telling me if throwing the particle, it will be rotating, in this case, in a counterclockwise direction. 逆时钟 in this case. Okay? use your right hand. Your 4 thumbs denote where the field is rotating, but again, this thumb is pointing in the direction normal to it. Right, so are we clear up to now? Okay, so take a look at the definition and try very hard to link to what I taught you in basic vector analysis. dl and delta s, what do they stand for? When you try to evaluate the net circulation, your vector field is making an inner dot product to the differential length. So this is telling you, whenever you choose a different orthogonal coordinate system to work with, you would have additional terms, right? Cartesian, the easiest. Spherical coordinate, the most difficult. But once you understand DL, you know everything. Okay, so later on, I will try to derive the expression for curl operation in Cartesian coordinate. Why? It's the easiest. And because you are smart, so I trust you, you can work on cylindrical and spherical coordinates. But again, you have this net circulation divided by differential surface. So again, there's no need to memorize anything once you understand how differential length, differential surface can be derived through your understanding. Everything is based on definition. So curl operation is trying to find the maximum net circulation. You want to find its direction and you want to find its magnitude. All right, so this is the formal definition. Let's look at one typical example. We have some vector field. Vector field has its subcomponents. So I'm working in Cartesian coordinates. So I have the x component, y component, and z components. But each component is itself a function of x, y, z. Right? Ax is space dependent. Ay is space dependent. Az is space dependent. So if I'm interested to find whether this vector field has a circulating component, I can form a closed loop. And that closed loop encompasses a surface. Once again, a surface in the language of vector analysis is a vector. So this closed loop is indeed a small surface. The direction points in the positive x direction. So that once the direction is pointing in x, you know its area must be defined by differential length in the y direction and z direction. Okay? So, in this case, I first want to evaluate segment number 1. So this differential surface has a closed loop defined by 4 segments. 1, 2, 3, and 4. And this surface is centered at x0, y0, z0. So this means if I want to know the net circulation over this closed loop, I have to calculate 4 times. I need to evaluate the circulation along segment 1, segment 2, segment 3, and 4. So what I'm trying to do is I want to evaluate the work done over segment number 1. So work on segment number 1. So this is your field making a dot product with differential length.
for segment number 1. So ask yourselves how to start. All you need to know is how to properly formulate the differential length in this case. So in this case, segment number 1 is pointing upwards, which means the unit direction is in the positive z direction. Positive z direction, and with a length of delta z. So since for segment number 1, the unit direction is z direction, which component of the vector field is being sampled? Or which component of vector field A could give you work and could give you, therefore, could give you circulation? Can X component and Y component really push you in the Z direction? No. Because you're making an inner dot product. You're walking along the direction in the positive Z direction. So the only potential being pushed by the field is by its Z component, right? AZ dot AZ gives you something non-zero. So you are essentially trying to evaluate the Z component. How strong is the Z component? Okay, so the work done by vector field A is only the Z component multiplied by this differential length delta Z. But the question is, this segment has its Y position having an offset. The entire surface is centered at x0, y0, and z0, but this first segment is having an offset in the y direction by delta y divided by 2. So this means, essentially, what I'm trying to evaluate, the work done along segment number 1 is the AZ component with its proper offset in the y direction and then multiplied by delta z. But this is not new. We know how to deal with it from last week. All we have to do is perform Taylor's expansion, right? So to properly evaluate this one, be careful. The AZ component, I want to evaluate the AZ component, but now the offset is in the y direction. So that means I need to evaluate, this is equal to the evaluation of AZ at the center point plus partial differential of AZ component, but in y. I want to know the slope of AZ component with respect to differential changes in y evaluated at the center point, but then multiplied by my offset in the y direction. And then the entire bracket is multiplied by the differential length, the total magnitude, delta z. As you can see, delta y multiplied by delta z gives you the area. Okay? So for the work done by the vector field along segment number 1, the only contribution is from the AZ component because your differential length is in the z direction. And it is this big. And that delta y divided by delta z is your unit surface area. That is your delta S. Okay, so as I mentioned, we need to evaluate the work done over 4 segments, 1, 2, 3, and 4. So at this point, which other segment do you want to calculate? Do you want to calculate segment number 2, 3, or 4? PA says, I want to calculate the work done by over segment number 3. Why? Because as you can see, segment number 3 is also having similar direction in the z direction, but it's negative z. So these two can be directly compared, right? If you want to have circulation, 1 and 2 are orthogonal, they cannot be compared. But this one and this one, if they cancel, you have no circulation. If they don't cancel, you have net circulation. So the next segment I want to investigate into is segment number 3. So I want to investigate the work done by the vector field when I walk along segment number 3. So I walk starting from the top and towards the bottom. So in this case, dl is having a reverse sign. So now it's pointing in the negative z direction. Negative z direction. But the magnitude is still delta z. All right? Now, of course, for this segment, it is offset negatively in the y direction by delta y divided by 2. So it's having a negative offset in the y direction. And our dl, differential length, is now pointing downwards. It's having a negative sign. So again, we perform Taylor's expansion, and we'll arrive at this formulation. So basically, the work done when you take segment number 1 is having a positive AZ, right? Plus a positive partial differentiation. As you take your segment number 3, the first contribution is having a negative sign. So W1 plus W3 have this term being canceled out, but essentially you have a non-zero term. So that tells you when you add the contributions of the works done over segment number 1 and 3, you do have potentially a non-zero result. So this is a point where you have to think. For this to be non-zero, your delta S is of course non-zero, right? You have an area. So the z component in this case, when you make a partial differentiation to the y direction, although it is a z component, but it is a function of x, y, z. So your partial y has to be non-zero in order to give a non-zero result for these two segments. So think about it. Let's come back to this. If this is your z component, AZ, it is unidirectional, and maybe its magnitude is only z dependent, right? For example, in this case, this is z, z. Just for example, your AZ component is in the z direction, and its magnitude is defined by its z position value. So in this case, your AZ making a partial differentiation to y is 0. Therefore, there's no work done when you walk in a closed loop. Okay? So the conserved field, you only have a unidirectional field. You cannot have net circulation. So I don't want to repeat for the other two surfaces, but for each direction, if you want to find the net circulation, you have to form a closed loop. So total together, you have 3 differential surfaces, and you have to calculate or evaluate the works for a total of 12 segments. But for simplicity, everything you do should just conform to what you have learned, okay? So whenever you calculate the work over one direction, you would have one partial differentiation, right? So for the work done over 2 and 4, that will pick up AY making partial differentiation to the Z direction. Why? You walk over segment number 2, you're walking in the direction of negative Y, right? You're walking in the direction of negative Y. But your offset is in the Z direction. So as you walk, you're trying to evaluate how much AY is having some circulating component, and you're making partial differentiation in the Z direction. Just take a look. You're walking in the direction of Y, positive Y, negative Y, but your offset as compared to the center is in the Z direction. So the Z goes to the partial differentiation. The direction is defined by your segment direction. So now, why do you have the negative sign? Why do you have the negative sign? Because for segment number 2, you're having a positive offset, but your direction is negative. Okay? As compared to this one, you have a positive direction, and you also have a positive offset. So you have a positive sign. But whenever you have a positive offset, but then you have a negative sign, the entire derivative picks up a negative sign. Right? Okay, so eventually, this is something you learned in the past. If you want to perform a curl operation in Cartesian coordinate, you only have to write x, y, z unit vectors, partial differentiation, del x, del y, del z, and you write down the 3 components of the vector field, ax, ay, and az, and you just calculate the determinant. It's easy and straightforward, but the reason is, as I showed you, we can calculate the net circulation by the definition, and eventually it ends up in this very elegant form. But this is only in Cartesian coordinate. You can try to work on the other 2 coordinate systems on your own, but let me spend some time and talk about the generalized formulation. The definition of curl is trying to find the maximum net circulation. When you try to find the circulation, you need to make inner dot product of your vector field with the differential length. So when you're working in different coordinate system, differential length, if your unit vector is angular, your differential length dl is an arc, right? And then divided by differential surface. So take a good look at the generalized expression for curl of A. This is generalized. H1, H2, H3 are the Jacobians. For cylindrical coordinate, 1, R, 1. Spherical coordinate, 1, capitalized R, R sine theta. So take a good look for 30 seconds and ask yourselves why the generalized expression is formulated in this way. I'm using the colors red to represent red, blue to relate to the differential length. Differential length if your unit vector is angular. You are spanning an arc. So for example, you're working in cylindrical coordinate. In the d phi direction, your arc length is r d phi, so you have to multiply this Jacobian into it, okay? Delta S needs to be divided, so H1, H2, H3 gives you the value, so you need to cancel out, right? For this one, H1 is cancelled out, so you divide by H2, H3, meaning you have a surface. In the first direction, its magnitude is defined by the differential length in the second and third directions. So again, once you have a complete understanding towards the cylindrical coordinates, spherical coordinates, once you have an angular unit vector, it spans an arc. So that is the difference in H2 and H3. So you can use this formulation based on your understanding to the definition of curve. Right? So are you okay on this? Students online? We still have 9 minutes. So before I move on to Stokes' theorem, I want to make sure all the students are comfortable with what I covered. Any question from the audience? No, not yet. Okay, so let's move on. Stokes' theorem is very similar to divergence theory. From the definition that we just covered, curl operation is trying to evaluate the net circulation over a very small surface area. So this is working in the microscopic view. For example, I have a very big surface. But when I perform this curl operation, I'm asking myself, oh, do you have net circulation in a very small surface area? Meaning, I'm dividing my entire surface into many, millions of very small surfaces. And each one of them, do I have a non-zero circulation? But eventually, all that I care about, in the practical sense, is over the microscopic view. If each small area is giving me some kind of net circulation, I really care about what is the total circulation for the entire surface, right? So I can move my differential surface to the left-hand side, and then I perform integration for all the surfaces. That's what I'm doing now. I evaluated the net circulation for each differential surface, and eventually I want to add them all up. So I perform a total surface integration. Surface integration, two-dimensional. But Stokes' theorem is telling me, you don't really have to go all those trouble. If you want to know that result, you can simply evaluate the vector field, making a dot product with the closed contour. For example, this is a net, a fish net. So eventually I have the outer closed loop. So if I want to know the total net circulation for the entire net, all that I have to do is calculate the circulation on the outermost part, that closed contour. So again, this is reducing your work. You start with, initially you thought you have to perform surface integration, but it's downscaled to contour integration. So this is easy, and they would have the same amount. So how to understand it? How can these two be equal? Let's take a close look. So over this fishnet, I divided into millions of small differential surfaces. For example, each surface is represented by 4 segments. When I try to evaluate the net circulation for this guy, right, I'm using my right-hand rule. So I'm evaluating the work just like I showed you. All the segments have a well-defined direction, right? For this case, all the segments are defined, so eventually they're working in the counterclockwise direction, so the thumb points outwards. But then the question is, for example, for this one, when I move to the surface adjacent to it, there would be one side which is common, right? But in this case, I still want to preserve the direction. So this segment, this very same segment, is taking on the positive sign when I evaluate for this differential surface. But when I evaluate the circulation for this surface, that same segment needs to point downwards. So eventually they cancel out. So does this two cancel out, cancel out. So everything's being canceled. The only thing not being canceled is the outermost contour. Okay? So this is the physical meaning of Stokes' theorem. Instead of calculating a lot of components, the work done on the small segments that will be canceled out, you only need to evaluate the work done over the contour, which will not be canceled out. This is, in essence, having the same philosophy as divergence theory. So go back to the last class, go back to divergence theory, and ask yourselves, what are the differences? The meaning, the process are having the same meaning, where you can reduce the integration's dimension by a factor of 1, by an order of 1. But here, you're involved with curl operation. So essentially, to me, in terms of mathematical approach, they are very identical, but they're trying to sense different fields. Here, you're trying to evaluate the circulating field. For divergence theory, you're trying to evaluate the flowing out fields that flows out. Okay. All right. So I should stop here. Let's take a 10 minutes recess, and then we can come back. So for the next class, we are going to finish vector analysis, and we will move on to electric field, finally. All right, let's take a rest.
那个前面甜甜的，后面苦苦的。
它那个感觉就是中药吧？
对啊，好。天哪！
可是那个味道也不会说大火，不知道怎么。耶，健康。
今天有超过9个人吗？
已经20个。
哦哟，不简单哎。现在还有在 streaming 吗？
我把声音关掉了，应该吧，应该没听到。
接实体线应该品质好多了吧？
就是它好像不会有时候突然卡顿，就是过去有时候可能大概会突然跳，然后整个画面会混掉。今天是这个状况比较少。
那为什么一开始你说会听不到？
好像因为因为之前跟之前不一样，所以他好像要去设一下他的麦克风到底要收哪里，因为他好像刚刚同时收到这个跟这个内建的，所以他刚刚这里都是杂音。
你用这个吧，这个比较高品质，你就选定都用这个。
对。
你们要严肃的去思考怎么考试。因为我到目前为止问过很多老师，大家都无解。
老师，你什么时候要考试啊？
第2份作业好像是4月8号交吧，那理论上你们1周改完，所以可能4月中。
因为我现在的想法是，就是变成让你带回家写，但是你就是可能，假如说你有出个6个题目，然后抓5题，然后这5题就是再乱数排列，所以这样就有很多份考卷，每个人拿到考卷都不一样，但其实是写一样的东西。然后可能我9点上手，然后让12点前交，这是我自己的想法。
要12点过去，
然后 Pro 是说他是说有一个然后用线上考试的方式，对，那个我就可能在问他的想法是怎样。我的想法是这样的，然后我们可以不用花那么多时间，然后就是时间到开放，然后再翻写。然后我觉得，就是如果说要抄袭的话，这个就
学生怎么拿到他的考卷？
就是发公告。如果说要看研究一下，那可不可以每个人就是不一样的？
对，可是你是要 email 给他们，还是他们
应该是
登录什么东西
？ILMS 那边吧，因为交作业也是在那边交。
有没有办法，同样的题型，只是你们数字不一样？比方说，有3组数字，然后 random 这样排序，这有很多份，但是你要怎么确保他答的题是哪一个题？
不然就是 ABC 卷，然后照尾数这样算。
ABC 卷照尾数。
对，然后就直接发，然后跟他说可能什么尾数写这个，什么不写这个。
那这样变成你们一个人改一个卷，懂？
如果要这样的话，
这可能是一个比较好的方法。ABC 卷同样的题型，但是数字不一样。他们如果要作弊的话，也就等于重新算。
对吧？
就等于是重新算。
可是 它只要因为如果说你要发3卷，就等于说你是要看学号尾数或者是怎样去算。但我觉得他一定有办法找到那个人，如果他们真的有心要作弊的话。
对，可是时间基本上还是2小时。
对。
如果在这个时间有限的我现在担心的是网络哦，会有人跟你说啊，老师我写好了上传，
就是可能
网络挂了，他就跟你凹，
多开半小时吧。然后不然就12点关了，然后没有交，就是12点半前直接交资本来找我。
我们总共65个学生。
对。
如果是你按照尾数，可能不会是正好4/3各21个学生。
对。可能要再去看一下他，因为他好像有些是别的年级。
对，所以你可能要自己 group 一下。你就要 group 这一组是哪一份题目，可以3组人，你自己挑定是哪3组，然后他们就会收到这一份考题。对啊，因为我是怎么样都想不出来到底应该怎么做。我不想用线上那种题目出，因为我觉得那个很难出。那你说出3份卷，我觉得是好的。那最传统就是找个晚上3间借起来，每一间只坐20个人。这一间是3间里面最小，这一间的 capacity 是103，那边是135。所以如果说100个人的座位，只坐20个，应该可以梅花座大家隔很远。对啊，你们回去讨论一下，明天 group meeting 的时候跟我讲，好不好？这个一定要决定的，因为大概是4月中考试。这一周过去就是清明节，就下周就是4月6号、8号，基本上就快要。
再下礼拜就考试。
差不多，再下礼拜就要考试，所以，我问到计算机中心的主任，他跟我说就不考。不考的意思就是纯粹 homework 100%，因为也没想要考，只有 homework。还有另外一个方法，有没有可能做 project？ 比方说他们自己找每5个人一组，交 project。这个很难改，非常难改。
对。
而且成绩不会，你看不出个人的成绩，所以我不是太倾向这个。那你说完全作业，好像也不是太公平，因为有些人临场反应就是比较好，有些人
慢慢写就会写得很好。
对，那有些人可能就是反应快，他可以马上就，我觉得还是要考试的。我倾向是还是要考试，但是真的实际执行怎么执行，你们明天3个人跟我 propose 一下。好。All right. There are 2 more topics.
topics we have to cover before we can close vector calculus. I want to refresh your memory about scalar Laplacian and vector Laplacian, but I want to most emphasize on two null identities. So first one, scalar Laplacian, by definition, it works on a scalar field, but the writing system implies you are making a twice differentiation. So whenever you see this delta function, capitalized delta, it means differentiation, and you have it squared. So you're trying to perform a twice differentiation on a scalar field. So the scalar field is defined as V, and the first operation, the first differentiation you're operating on a scalar function should be therefore gradient. So once you perform the gradient, in Cartesian coordinate, gradient is giving you a vector. So the x component is your scalar field making a partial derivative in the x direction, and then the y component is del v del y, z component del v del z. So essentially you have a vector. Scalar Laplacian implies you start from a scalar, you perform a twice differentiation, but you arrive at still a scalar. So now you have a vector and you want to perform differentiation and you arrive at a scalar, so the only choice you have is divergence. Okay, because essentially in Cartesian coordinate, we know that divergence is trying to apply differentiation for all the components and you add them up, so you arrive at a scalar function. So the scalar initially becomes the vector after performing gradient operation, and then the vector is applied with divergence operation, you arrive at scalar. Okay? So in Cartesian coordinate, scalar Laplacian is nothing than your scalar function making a double differentiation in both x, y, and z directions. So now we can move on to vector Laplacian. The definition is quite complicated, right? So this is for you to memorize. But in Cartesian coordinate, it's easy. It's just each component, after you perform vector Laplacian, you operate on the vector and you arrive at a vector. So the x component is just the x component of your initial vector performing a scalar Laplacian. Okay, so you add this all up. So how many terms do you have in total? This is the scalar Laplacian. It contains 3 terms, 3 double differentiation terms. Right? For each one of them, you have 3 terms. So you total have 9 terms. So it can be complicated. But this is some operation that we will use in the later part of this class. Okay, just remember it. For now, you probably don't really need it, but yeah, in the last chapter for this class, we are going to use it heavily. So I will try to refresh your memory by that time. What I want to emphasize for this class is the 2 null identities. Null means 0. So there are certain type of vector operations that would guarantee you have a 0 result. So the first one is, if you have a scalar field, you perform its gradient, and then you perform its curl operation. It is guaranteed to be 0. I'm sure you learned this already, I mean for many times, but you don't really know how to understand it, and therefore you cannot remember it. So I think my job function is to help you to understand it in a physical sense. We just talked about curl operation, right? Gradient over a scalar function gives you a vector. So the curl operates on the vector, but why is it always 0? How can you understand it? So my job function, let me try to help you to understand it. For example, I'm trying my very best. If you understand what I'm drawing, do you know what I'm drawing? Taipei 101. Taipei 101, you have a lot of floors, right? Different floors. 101 floors. So each floor is having different height or different potential. So I call this height as my scalar function v. V equals the height. So if you perform gradient of v for Taipei 101, which direction would it point to? The change in height, right? Gradient means the maximum amount of change and in which direction. So if height gradient v for Taipei 101, right, points upwards. You ascend, you gain in height and in that direction, in the shortest direction, normal to the floors. So now you have to think. Now you want to perform the curl operation on the gradient. This is a unidirectional field, right? It's unidirectional. So if you walk in a closed loop, there's nothing to give you net circulation. If you walk on the same floor, gradient of v is perpendicular to your closed path. You don't gain anything, right? You're walking on the same height. You don't gain any potential. And because this grad v is unidirectional, even though you walk in a closed path, this work will be canceled by this work. So they cancel out. So essentially, I'm trying to help you to understand the meaning of this one. If you have a field, a vector field, which can be written as gradient of v, this field is most likely unidirectional. It is a conserved field. For conserved field, you do not have net circulation. And net circulation means curl operation. Okay? So try to understand it, try to embrace it by physical meaning rather than just by mathematical formula. If you have a conserved field radiating or unidirectional field, like the graph V I'm showing you, it cannot give you net circulation. Just think of the height, think of gravity. They don't give you non-zero result when you start from one point and you come back to the same point. So the physical meaning is a conservative field. When your field, vector field, you take its curl, it's 0, that vector field is conserved field, like the height, like the electric field actually, okay? Like gravity. Another way you can appreciate is the radiant field, a unidirectional field. Unidirectional field, right? Like a ray shooting out, radiant. has no net circulation. Because when you take a closed loop, there are segments that are forced to orient in a negative direction. But your field is only one direction, unidirectional. So the work done on these two paths will be canceled out, giving you no net circulation. All right? So the better way to understand this null identity is the curl operation on the gradient of a scalar field. The gradient is trying to find the maximum change. So it's perpendicular to your surface. Okay, so if you walk on this contour, there's no contribution. And because you perform the gradient, the resulting vector field is unidirectional. Right? Second null identity, divergence of a curl is always 0. How to understand it? Well, curl operates on a vector. So the apparent difference as compared to the first one is this one operates, you start with a scalar field. But this null identity is focusing on a vector field. Think about it. What is the physical meaning of divergence? Curl of A is a vector field, so you can apply divergence on it. So if you have a vector field and you try to evaluate its divergence, what does it mean? Divergence, again, is trying to measure the net outward flux within a small volume, right? Like a flow of water, the magic water faucet that I showed you. But what type of operation is curl trying to sense? If you have a vector field, you perform its curl operation and it is not 0, which means now you should be able to understand it and explain to me. If you have, so this curl of A is not equal to 0, right? Your curl of A is not equal to 0 means you have a circulating field, right? You have a circulating field, but now you're asking me to evaluate the divergence of the circulating field. Just imagine, I have a box. I have a magical box. I open the box, I have something circulating inside. Okay? So you ask yourself, oh, I have a circulating field inside the box, so how much of that field is flowing out of the box? 0. Right? By performing this curl operation, you're trying to find the components that gives you circulation in A, right? So after you perform this operation, you only have a circulating field, and now you want to have a box to surround it, and you want to have fields flowing out. It's impossible. So this second null identity means divergence. You're trying to sense fields flowing out, but unfortunately, you performed curl operation first. You try to find the components of A that's circulating, so it's not flowing out. Right? So these are the physical meanings behind these two null identities. So if you understand divergence operation, you understand curl operation, you understand gradient, these are actually very natural. Again, divergence of a curl is equal to 0 means you have circulating field, right? Once you have circulating field, there is no divergence. So try to read this sentence. Divergence free means divergence of the vector field is 0, means divergence free. It is a circulating field. A circulating field in a more academic nomenclature is a solenoidal field. So a solenoidal vector field can be expressed as the curl of another vector field. This is too deep. Okay? This is for you to come back and read. So as we move into magnetic field, this will become important. But for now, I just want to tell you a vortex field or a circulating field is like a vortex, 漩涡. Okay? A circulating field, a vortex field, has no outward flux. Right? Circulating field, like a vortex, 漩涡, does not flow out. So the physical meaning is if you have a vortex field, its divergence is 0. If you have a radiating field, it is derived after performing gradient over a scalar function. There's no curl, there's no net circulation. Right? Other questions? If not, we are going to close vector analysis, vector calculus, and we're moving on officially to electric field. Alright, so before we go into the electric field, let me just copy down the two new identities we just covered. So the curl of a gradient of f, a scalar function, must be 0, and the divergence of curl of a vector field would always be 0. Okay? Okay, so you worked hard. Finally, you were launching into the official content. All the previous topics are more like a background information. Yeah? Question?
讲义是有跳一页吗？
Right. There is one last page on the previous chapter, which I skipped because it's not really giving you a lot of information. But you can keep it. You can just read it on your own. It's just saying a field can be comprised of two parts. One is conserved, one is non-conserved. Because eventually the curl operation and divergence operation, they are commutative. So basically it's just saying that a field can have two components. Okay? So if you perform divergence, the conserved field, the conserved part will give you a non-zero divergence. On the other hand, if you perform the curl operation, the non-conservative part will give you a non-zero result. That's it. It's just a linear superposition. Okay? But thank you for your question. Does that answer the question? Yes? Okay. All right, so now we're moving into the textbook, chapter number 3. It's entitled Static Electric Field. So I prepared 3 PowerPoint sets for this chapter. So the first PowerPoint set is discussing about electrostatic fields in free space. Free space means there's nothing. In the space considered, there's nothing. Vacuum, right? So the structure of the textbook and for our following class is we are going to investigate into static electric fields. Okay. Electrostatics means static electric fields. And then the next topic is static magnetic field. Right? Then in the very end, we are going to combine these two, electric field and magnetic field, to electromagnetic field and time varying. So when you have time variation, you really have a wave. Right? Think about the transmission line you learned. We have a wave. A wave depends on time and location. But it is easier for us to understand static, meaning there's no time variation. So in the end, we want to understand how a wave behaves, but before that, we need to have deep understanding to the statics. Now the way the textbook is trying to describe E field and magnetic field is, for each field, it teaches you electric field in free space. There's nothing. Okay? So my first hard point set is electric statics in free space, and then electrostatics having materials. What are the effects? For example, you have electric field in water, in glass, in silicon. What are the differences? Third PowerPoint set will be focusing on boundary conditions and electric energies. Right? So 1, 2, and 3. So these divisions would also apply to magnetostatics as well. Right? So there will be 3 PowerPoint sets for electric fields and another 3 for magnetic fields. Okay, so today, according to time, I could probably cover up to fundamental postulates and maybe Coulomb's law, maybe. So there are 2 fundamental postulates, only 2. And now you have to think, this is based on your maybe previous understanding to electric field, but I really want to relate our understanding to electric fields to the 2 null identities. It happens to be that the very reason we emphasize on the null identity is it's strongly related to the field distribution. And I can give you a hint. One of the null identity is directly related to electric field, and the other one is directly related to magnetic field. So before I reveal the secret, take a guess. Which one of the 2 null identities is related to electric field that we are talking about now? Before we move on, we need to make assumptions. Okay? So in electrostatics, the basic assumption is nothing is moving. Right? Static, 静态, stationary, everything remains not moving. Right? So everything is not moving. And we're talking about free space now, so we might have vacuum, but we have one charge and the next charge. But they're not moving. Nothing is moving. Okay? And at this moment, there is only electric field in the space, in the free space. we only have electric field. So we only consider electric field intensity E now. This E is a vector. So later on, I will refer electric field as E field. Okay, whenever I mention E field, I'm talking about this capitalized E vector. The official name is electric field intensity. All right, the definition of E field or E field intensity is, well, just imagine in space, right, in free space, if there's already some type of electric field, E field, and I have a charge, a particle that has certain charge. This charged particle positioned in the space filled with electric field intensity would feel some kind of force. Okay, so that is called electric force. So that electric force divided by how much of charge I'm carrying defines how strong the E field intensity is. Okay, so this is just a formal definition. So the force is proportional. So the force is proportional to how much charge you carry and multiplied by that E field intensity. Okay, so this definition is just general, right? You should have no question about it. But then, what's really relating to the physical understanding is the first postulate, written in differential form, directly tells you divergence of the E field intensity is equal to something. Oh, this is important. Why? The very reason I spent so much time teaching you and describing divergence is meant for you to relate to the electric field intensity. Divergence of the E field intensity is equal to rho divided by a constant. Rho here is the volume charge density, Coulomb per meter cubed. Or within a value, how much charge do you have, right? That's rho. So how much charge you have divided by the volume, that is your volume charge density. Epsilon 0 is just a defined constant. It's called the vacuum permittivity. It's just a constant. But look at this fundamental postulate and ask yourselves, if you have a single charge, sitting in space, not moving, what would its E field intensity look like? According to the equation, divergence of the vector field is equal to a scalar, and that scalar tells you how much charge you have, right? Just by this simple postulate, the simple divergence relation, you already are capable of drawing some picture of the resulting field distribution. Again, tell me, what is the definition of divergence? It's too bad I cannot hear you. Otherwise, you would be saying that divergence is trying to find the net outward flux of that field over a given volume, right? So under this postulate, this is already telling you we know how the E field intensity looks like if you have a single charge. It is radiant. you have a charge here. Once you have a charge, the fields would look like something radiating or shooting out or shooting in, depends on the sign of your charge. If you have a positive sign, if you have a positive charge, you have rays of electric field intensities, and these are called E field lines. 电力线, E field lines shooting out. Let me draw it for you. So if you have a positive charge, right, you would have E field lines shooting out. And it's not just two-dimensional, it's three-dimensional. It's also shooting out into your eyes, right? So you have a single charge, it's just like sun. Just like sun having sunshine, right? So the physical meaning is the E fields are radiant for a point charge. How do we know that? Because divergence tells you if you have a positive charge, you would have net outward flows, right? So everything is natural. What I'm trying to give you is your ability to form a physical picture just by looking at a mathematical equation. Divergence tells you have to go out. So if you have a positive value, your field lines are shooting out. So what happens if your charge is negative? Then your divergence is flowing in, right? Your fields are flowing in, and therefore your charge is negative, field lines going in. Again, everything is three-dimensional, okay? So that's the first fundamental postulate. For electric fields, divergence, once you have the field, divergence is not zero. What does that imply? And look again at this equation. What is the source for electric field? This equation also tells you once you have a charge, you have field, right? So the source for an electric field distribution is charge distribution. Secondly, it tells you if you have a single charge, you have a sun-like radiating pattern. Okay? Now think, if you have a radiating, well, for example, you have a single charge and you have a radiating E field pattern, what other mathematical description or physical description would you be using to describe it? So in my personal opinion, you only need to understand the first postulate and then you understand the second postulate. They are actually saying the same thing. The second one, well, let's come back to the null identities. Divergence is not zero. What does that mean? And the field divergence is not zero, and I'm telling you everything's radiating outwards in a unit direction. This implies electric fields are conserved fields. just like gravity. So the second one tells you, since your field for a single charge is radiating, like how sun shines, coming out of sun, so the curl is 0. These two are like twins. You have one, you must have the other. Okay. So curl of E field is 0, means electric fields are conserved. Right? So the physical meaning is they are conserved, so they are not rotational. There's no circulating component. For electric fields, you don't have really circulating components. If you do have circulating components, it's not conserved. All right? Then curl of E is not equal to 0. And that violates our understanding. Right? So this is coming directly from this. You have radiating field patterns, so you don't have circulating fields. Therefore, curl of E is 0. Definite. Right? Now, can you answer my previous question? I told you, electric field is associated with one of the null identities. So there are two. I'm such a nice teacher, I'm telling you the answer. Curl of E field intensity, a vector, is always 0. So you, at this moment, should be capable of relating that to the null identity. Curl of a vector field is 0, so that vector field can be written as the gradient of a scalar function. And that scalar function is potential, voltage, that we always talk about. Okay? So electric field is associated with the first null identity. Magnetic field, on the other hand, is related, or directly related, to the second null identity. So if you're smart and if you understand my lecture contents, you should have a physical picture now. E fields are radiating out. Magnetic fields are circulating, right? Straightforward. Vector analysis is telling you a lot about our world, okay? Now, these two postulates, divergence of E is equal to rho divided by epsilon 0, and curl of E is equal to 0, they're universal. So no matter which orthogonal coordinate system you decide to use, they always remain true. Okay? They're always true. Now, knowing the differential form for the two postulates is really not helping us a lot, right? Because eventually, we should be capable of calculating the fields, the E field distribution, as a function of space whenever we know the charge distribution. But the differential form is not giving a lot of information. So for this particular case, we want to know the macroscopic description of E field intensity, which means we want to have the postulates expressed using integration, right? So again, differential form tells you the microscopic, point by point, what is happening. But the integral form means overall, I can just describe it, okay, in a macroscopic view. do we have the mathematical tool for that? It's still here. Because E field is associated with divergence, so why don't we invoke divergence theorem to give us a nice and easy fundamental postulate in integration form. So divergence of E is equal to rho, the volume charge density divided by the constant. And because you're so smart and you're so hardworking, you learned very solidly, so you know that we already covered divergence theorem. Divergence theorem tells us if you want to evaluate the divergence point by point, and we integrate over the entire value. So point by point, I know the divergence, but over the entire value, do I need to perform the value integration? No, we don't. We only need to evaluate the vector field making a closed surface integration to evaluate the same thing, right? So now we replace A by E. So divergence of E is equal to rho divided by epsilon 0, and we perform the value integration. This is easy because that's the total charge, right? So Gauss's law is basically saying the fundamental postulate, the very first one, if you know how much charge you have, basically you know how your E field distribution would look like. Okay, this is extremely important. Using this integral form is much easier for us to derive how the E field distribution looks like. Differentiation form is looking at the microscopic view. It's not really helpful. So Gauss's law is nothing more than the first fundamental postulate, but using a different viewpoint. This is microscopic. Gauss's law is a macroscopic 巨观 point of view. All right, curl of E is equal to 0. Why do professors always teach divergence theorem and Stokes theorem? Because they're useful. Whenever you have curl operation, you use Stokes theorem, right? Instead of calculating the curl over the entire surface, you only need to evaluate the field over the closed loop. So we apply Stokes theorem. This A is replaced by E. Curl of E equals to 0. So that means when you have electric field, you walk in a closed path. This is 0. It's always 0. So again, this is telling you electric fields are conserved fields. So in this electric fields, you walk, you start from a certain point, you walk whatever path, you come back to the same point, you gain nothing, you lose nothing. It's conserved. Okay? So how can this be really applied to our daily lives? It's like saying nothing, right? It's just saying the field is conserved. But it's saying a lot. If you still remember, in electric circuit, you learned about Kirchhoff's voltage law. Oh, that's extremely useful. This is equivalent. E field making some work means your energy or potential. It's like voltage. So basically, if you have a closed loop, all the voltage drops would sum up to 0. So that is equivalent form of Kirchhoff's voltage law. So the second postulate directly contributes to Kirchhoff's voltage law, right? So I think time's pretty much up, and instead of going into a new section, I would rather stay here and see whether you have questions. So on Wednesday, we can pick up the progress from Coulomb's law. So are there questions from the distant audience? No? Okay, everything clear, so I'll see you on Wednesday. So I hope by changing the PowerPoint, by changing the text size and changing to a real internet connection, the streaming quality is now better. And I think for the filming crews, they are more comfortable now. Okay, so see you on Wednesday and thank you.对，但是 Stoke 是有点把二维变成一维，对，因为它是从面积分变成是线积分，对，
就是那个就是选
对。理论上就是说，一般人大概会用是一种数学工具去理解它，但我个人认为是在